So if you recollect, we were looking at single sideband modulation yesterday, and we learned how to demodulate a single sideband signal. We also learned how to generate a single sideband signal using either the sideband filtering method or the phasing method, right? And the phasing method was based on a new representation of the single sideband signal that we discussed, which involved the message signal MT, the carrier cosine omega ct, and the quadrature carrier sin omega ct, along with the Hilbert transform of the message signal, right? So that representation also led us to an alternative method for generating SSB signals, right? Now we were also looking at the demodulation, and when we were discussing the demodulation, we found that the demodulated signal, when you do coherent detection, is given by in the presence of, let's say, lack of synchronization between the local carrier and the incoming signal, incoming carrier. Your demodulated signal would consist of a component due to MT plus a component also due to M hat T, right? So unless theta T is 0, this would lead to severe distortion, right, in the recovered message signal. If theta T is not 0, right? So this is one small problem that we faced in the demodulation process in this case. Of course, if there is perfect synchronization, there is no problem. There is a second method for demodulation of SSB signals, and that's called the carrier reinsertion method. This also requires a local carrier like the coherent demodulator, the standard coherent demodulator, but has some minor advantages over that in terms of practical implementation, right? Basically here what we do is take the incoming modulated signal, and instead of multiplying this with the carrier, local carrier, you simply add it with the local carrier. Right? So you have a local carrier and you add local carrier to the incoming signal. And what do you think you will get now? Well, we'll see that if it is not obvious. We will get a signal whose envelope approximately under certain conditions follows the envelope of the message signal, right? Now it's not obvious at all. We'll see how it becomes so, and if this is indeed so, what we can do is follow this up with the envelope detector. To produce your detected output, demodulated output y sub dt. Okay. To see what happens, let us consider the signal ET at the output of this adder. What does it look like? It contains the SSB signal coming in plus the local carrier, right? So the SSB signal coming in and the local carrier, if you do that, if you remember, x of t is mt cosine omega ct plus m hat t sin omega ct, right? And you also have k cosine omega ct added to that. So the cosine omega ct has two parts now. The in phase part of the SSB signal was half AC mt, right? this was multiplying cosine omega ct, plus you have a constant amplitude carrier k here, and these two together now constitute the so-called in-phase part of the SSB signal. And what is the quadrature phase part? Well, depending on whether it is lower sideband, upper sideband, we'll have half AC m hat t into sine omega ct. Okay. One of the very nice advantages of a quadrature representation of this kind, remember we have discussed this quadrature representation for arbitrary narrowband signals, and it is interesting to see that the various kinds of AM signals that we have discussed, each of them fall into this representation, right? For example, the DSPSC signal has only one part, the in-phase part, right? Half AC MT cosine omega ct, right? Whereas the single sideband signal has both the in-phase part as well as the quadrature phase part, in which the quadrature phase part is the Hilbert transform of MT, right? So this falls in the general class. I mean, this is in conformity with our discussion on the general representation of bandpass signals, which has an in-phase part and a quadrature phase part. Only thing is that there is a special relationship for the between the in-phase and quadrature phase parts for it to become an SSB signal, right? That we have understood now. Now, one of the advantages of this representation is that you can easily identify what the envelope of the signal will be by writing this expression. If you remember what is the definition of the envelope, now the basic definition of the envelope was that we wanted to find out it's a trace of the positive peaks of the carrier, right? So to understand how we can identify the envelope, if we one can rewrite this as an amplitude part RT, which is always positive, into if cosine omega ct plus a phase part theta t. This signal can always be written in this form using trigonometric identities, right? For example, what will be RT? If you want to write this expression in this form, what would be the value of R of t? It will be the square root of the square of this plus the square of this, right? And that becomes your envelope. What will be the value of theta t? It will be the tan inverse of this upon this, right? So here RT is square root of half a sub c mt plus k whole square plus half a sub c m hat t whole square, and theta of t is tan inverse of half mt plus k of AC a sub c mt plus k upon half AC m hat t. Inverse of this? Yeah.
So the RC circuit is
okay. Right. So you can make this cot inverse.
So the diode in the RC circuit which we use for demodulation, sir, even there we used to get the envelope, but with pixels. Is that it?
No, I think you are not understanding the point that I am making. We are now looking at the envelope of this signal, right? The envelope detector will be the same. The envelope detector will remain the same, the diode detector, but we are not discussing the envelope detector here. We are trying to understand the nature of ET, right? That is our concern here.
And our aim is to get the signal back again.
That's right, but please give me some time to explain how it is coming back, right? I am just explaining that. Give me time, right? In any case, theta t is not relevant here. We are only looking at the envelope, right? So now let's look at this envelope. Let me complete my discussion, then I'll take a question from you. Is there a mistake I'm making?
No, sir. In the initial part, we are adding cos k cos omega ct.
Right.
And that is at the receiver.
Right.
And how are we generating this signal?
The cosine omega ct?
No, sir. Exactly the same, because it should have a phase difference also.
I'll come back to this point. That's a good question. The question is, we are not really, it appears, totally avoided the phase coherence issue, right? We are adding a local carrier which is adding up to the cosine omega ct part of the incoming signal, right? Which essentially means that you require a phase coherence, right? So that issue remains to be discussed, and we'll certainly come back to it. But first let us see how does it help us, right? So surely that's a relevant question to ask. Okay, so now let's look at this expression for the envelope. I would like the envelope to follow the message signal. Can I make some assumptions which will make it so? Under what conditions will RT approximately follow MT? When K is very large. Correct. So that's precisely what we'll do. We'll choose our local carrier to be added in sufficiently large quantity, with sufficiently large amplitude, so that this term dominates over the second term, so that this can be ignored in this squaring and square rooting process, right? So if we make the assumption that half AC MT plus K is much greater for all time than half AC M hat T, which can be easily done by choosing K to be a sufficiently large constant, right, with respect to these other signals, then we can approximate R of T as equal to half AC M of T plus a constant K, right? And therefore if you ignore this constant, we got an envelope which is proportional to the message signal MT, right? And therefore our envelope detector in that condition would produce an output proportional to MT. You agree with that? If the envelope follows the message, the envelope detector obviously would produce an output which is proportional to the envelope. Yes, please.
So in case MT is a cosine signal or sine signal, simply half AC square would be left, because MT had to be sine or cosine.
Whatever MT may be, it will be cosine omega, it will not be cosine omega CT, it will be cosine omega MT, it will be low frequency signal.
But sir, same way M had T, so both be cancelled and sine square and cos square.
No, if you look at this total expression is always going to be much larger than this, right? That is the assumption we are making, right? So I think there is no need to bring in that issue at all, right? This will be still valid, whatever the message signal MT may be, right? It will be still valid. So the envelope will follow this. So therefore this gives you an alternative method for demodulating SSB signals. Now that issue that was raised a couple of minutes ago, excuse me, that issue that was raised a couple of minutes ago about the phase coherence of the local carrier in this case, right? It's true. Even in this situation we would require the local carrier to be in phase and frequency synchronism. However, even though that is so, it is easier to manage than the local oscillator which mixes the two signals, right? It's easier to manage in the following way, in the following manner, that at least for applications like speech, for example, right, one can adjust this phase and frequency manually in this case till you get in your distortion removed and your intelligence. It is not as sensitive as it is in as the other case is, as the coherent demodulator is, right? So one can manually just like you are tuning the receiver, you can tune the receiver exactly to have a phase and frequency synchronism and till you get your speech quality back, right? It's easy to do it in this case than in the other case, right? And therefore this is preferred over that system, right? But your question is very much valid, but this is the answer to that question, right? So the local carrier frequency, let's say the frequency and phase in this case can be manually tuned to get the right quality of empty. And this is particularly doable when empty happens to be a signal which you can hear, right? Like speech or music, particularly speech. One doesn't use SSB for music ever, right? So typically for speech, till you get your quality back and the intelligibility is good, you can keep on tuning it.
Manually do it over here. You can manually do it in cos omega CT and multiplying it also.
That is what I'm saying. Theoretically it can be done, but that's a much more difficult thing to do than in this case, right? This is, in other words, if you do some analysis, you will find that this is less sensitive to the phase and frequency errors than the other system is, right? I'm not doing that analysis here, but there a slight phase offset will completely start distorting your signal because of the multiplication with the terms cosine theta t and sine theta t, right? Here it will not be as sensitive as it is in that case, right? So that's something that is known by experience, as also it can be shown by analysis. So see if you can work out what is the sensitivity of this demodulation to theta t, right? If you just attempt to do that and see what kind of conclusions you can reach, you will probably start agreeing with this, right? But if necessary, we'll take it up in our tutorial. But at the moment, I'll just make the statement that this happens to be the case, that it is easy to at least tune it manually for applications like speech transmission, right? Okay, so that's about single sideband modulation. Single sideband modulation is good if you want to save bandwidth. It's a little more tricky to demodulate, like we just seen, right? But it is, these complexities one ignores if bandwidth is of very major concern to us, right? We want to save bandwidth, we will live with the complexity, right? We'll try to do whatever is required to make the receiver working very well, but if the receiver happens to become very complex in the process, we don't mind, right? Because bandwidth is important. It's an important resource for us.
Sir,
Yes, please.
advantage of the quadrilateral carrier multiplexing, like in that also we are having the same bandwidth. So
There are two different ways of saving bandwidth, right? They are equivalent ways. Depending on the application, you'll choose one or the other, right? So if you have an application where you would like to actually transmit two messages on the same carrier, quadrature multiplexing is a good alternative, right? If on the other hand you're transmitting a large number of messages, maybe in the same overall frequency band, it's much more convenient to put each of them put the single sideband modulation, use single sideband modulation and put them in a large number of adjacent sidebands, because the quadrature multiplexing can handle only two signals, right? If you want to handle more than two signals, that philosophy will not be useful directly for multiplexing. Of course, you can do quadrature multiplexing in each band which is twice the single sideband. That also can be done. So there are various alternatives which are possible, right? We have a number of techniques available. Which technique you actually adopt will depend on the application, right? We'll consider some applications where frequency division multiplexing will enable us to put a large number of messages in adjacent sidebands, right? And we'll use a single sideband modulation, right? But before coming to that, let me discuss one more kind of amplitude modulation which is very, very pertinent in the context of suppressed sideband modulations. Okay? Now let's discuss the motivation for that first. This new modulation that I'm going to discuss now, if you remember, I classified the suppressed sideband modulations into two types: the single sideband modulations and the next one, which was vestigial sideband modulation. So I'd like to discuss this a little bit. First, the motivation. Why do we need such a thing? Before even telling you what it is. The need is as follows. Single sideband modulation saves us bandwidth, that is well understood. It however has one problem. Suppose we already know that your single sideband modulation is difficult to generate, because it either requires us to have very sharp cutoff filters in the frequency domain, right, around the carrier frequency, or else you require equally slightly less difficult but still difficult problem of realizing the wideband Hilbert transformer at baseband, right. These are the two ways by which SSB can be generated. Now when you try to do a sharp cutoff filtering at the carrier frequency, right, I don't know whether you have been involved in some filter designs. Typically the amplitude characteristics are best in the middle of the band of any filter. Similarly, the phase characteristics are also best in the middle of the band. But the moment you deviate from the band, typical filters that you will realize or synthesize or make will start to develop non-ideal characteristics when you go away from the center of the band. So around the edge of the band you will have both nonlinear phase characteristics as well as maybe not very nice amplitude characteristics, right. If instead of remaining absolutely constant, of course they will have some oscillatory behavior, or the phase characteristics will become nonlinear at that time, right. And so if your basic signal, message signal, has a significant amount of low frequency component, right, you understand, I'm talking about the baseband signal. If you have a significant amount of low frequency component in your message signal, where will it go after DSB-SC modulation? It will go around FC. That significant significant energy content at low frequencies would translate to significant energy content at around the carrier frequency, right. So now if you have a sharp cutoff there, and that sharp cutoff is associated with these problems, it will definitely distort the low frequency components of your message signal, because that is going to get affected by the cutoff characteristics near the FC, near the carrier frequency. So let me maybe illustrate by a picture. So let us say your message signal spectrum looks like this, right, and ideally if you had a sharp cutoff filter like that, if you want to remove the lower sideband, no problem, if you can do that. But this is precisely the problem, I can't do that, right. Typically what will tend to happen is that I might get, even if it is a good filter, it might be like that as far as amplitude characteristics are concerned, right, and the phase characteristics perhaps in this area would be highly nonlinear, because the sharper the cutoff, the more nonlinear it tends to become, right. So phase characteristics will tend to become highly nonlinear, which will imply some kind of a delay distortion or phase distortion of the low frequency components of the message signal. Why low frequency? Because these frequency components actually belong to the low frequency component of your original message signal, right. So if your message signal has significant low frequency content, right, then SSB will create all these problems for us because of the need for sharp cutoff, which either we can't do it, or if we can do it, it will be associated with these kinds of distortions. For certain kinds of signals, this is not a serious issue. For example, for speech signals, we know that the low frequency content is not that high. I discussed with you some time ago at the beginning of this course that speech signal has significant content from let's say 300 hertz onwards, right? It practically has no content between 0 to 300 hertz, right? So in that kind of a signal, the spectrum after frequency translation would perhaps look like that, right? There is a band here in which there is no signal energy, right? And that gives me flexibility in designing this filter. The filter design can be done. I don't need a really sharp cutoff filter, I mean in the sense of a brick wall characteristic. There is a band available over which I can gradually roll off the characteristics of the cutoff filter, sideband filter, right? Which is not going to be available to me if this band was not available to me, right? You appreciate this point? So in certain kind, and also there is a second point. As we discussed earlier, speech is a kind of signal in which even if some phase distortion occurs, it doesn't matter very much. Why? Because our ears are insensitive to phase distortion. The way the ear perceives speech, phase distortion or delay distortion is not very crucial, right? So therefore, for speech applications, SSB is quite okay. SSB is doable, right? In fact, in speech applications it is widely used, single sideband modulation. However, there are certain kinds of signals which have a lot of low frequency content, right, and which are sensitive to phase distortion. And one such set of signals is a picture signal I mentioned to you, right? So you have picture signals, you have facsimile signals, which are also kind of picture signals. You are scanning the content of a page, right? So all these signals are very sensitive to phase distortion, which will occur if you try to implement an SSB modulator, right? And at the same time, such signals have very large bandwidth. For example, a picture signal has a bandwidth of the order of 5 megahertz. We discussed that, 4 to 5 megahertz, and there is therefore a very strong case for saving bandwidth, right? The voice signal, after all, uses only 4 kilohertz bandwidth, right? So while there is a need to save bandwidth if you want to transmit a large number of voice signals, even one picture signal alone will consume, if you were to allow DSB-SC, 10 megahertz of bandwidth, 5 megahertz on either side, right? So there is a very strong need, a very strong case for saving bandwidth here. At the same time, we find that SSB kind of saving will not help because it will create undesirable distortions. So this is the motivation to look for something different, okay? And that's the motivation for vestigial sideband modulation. Is that okay? So basically let me summarize what I have said. What we have said is that SSB is suitable and implementable for what kind of messages? For those messages which have relatively less energy content at low frequencies, right? For messages, let's say with little low frequency and content. Because if that is the case, the separation of the sidebands, separation of the upper sideband from the lower sideband or vice versa becomes easy to do. Make separation of sidebands possible. This feature of this message signal makes the separation of the two sidebands feasible or possible. Right? I have explained this. I hope you understand this now. I am just summarizing. On the other hand, message signals having large bandwidth and significant low frequency component content exist, like the TV signal, the video signals, the fax signals, etc., the data signals, right? all these kinds of signals, they have significant low frequency content. So this separation becomes more difficult, and if you try to enforce it, it will create all kinds of distortions which are not acceptable. Okay? And it is for such applications that one thinks of VSP. Okay. So having motivated the need for a different modulation, what is it that VSB can do which SSB cannot do, which makes it a preferred modulation for this case? Okay, the VSB's approach is like this. All right, I will not be able to save the entire bandwidth because of this very difficult situation that the two sidebands are just meshing into each other, and there is no gap for me to design a graceful filter. Right? So what if I allow most of one sideband and a little bit of the other, so that the filter design becomes an easy job? Right? And that's basically the idea of VSP. So in fact that's the meaning of vestigial sideband. You allow most of one sideband and a small portion, or what is also called a vestige, of the other sideband. Right? So if you do that, our filter design requirements become much easier to handle, and all those distortions that were coming because of the sharp cutoff will not happen now. Right? So basically that's the idea of a vestigial sideband. It retains most of one sideband and a very small portion or a trace of the other. And that permits me replacing the sharp cutoff filter with a gradual roll off kind of filter, gradually rolling off filter. So what we are saying is, can be pictorially expressed like this. You generate your signal, message signal, you do DSP-SC modulation on this by multiplying this with A cosine omega CT, and you have a sideband filter here, but it is not that sharp cutoff filter. We will call it some H sub VSBF, which will yield the VSB signal. Typically it will be, if required, also send some portion of the carrier if required, but that's not important right now. Right? And this HVSBF, suppose we want the high the upper sideband, it will not now be a filter which has this ideal requirement, right? It will indeed allow a gradual roll off like that. So you will be transmitting most of the sideband, the upper sideband. Let's say the bandwidth is B, right? So this is F sub C, this is F sub C plus B, but you are also transmitting this portion of the lower sideband. Right? It could be the other way around. You could be transmitting the lower sideband, most of the lower sideband, and a small portion of the upper sideband. It could be either way. Right? Of course, the similar thing will exist on the negative frequency axis. So your bandwidth will now be, suppose basically we are going down on this side by a small amount. Your bandwidth B may be large. For example, in the TV case it is 4 to 5 megahertz, right? 4.5 megahertz or something. There will be an overflow into the other direction by an amount, let us say beta, right? Where beta will be typically much less than B. So you will be still saving a considerable amount of bandwidth, right? But you will be relaxing the requirements of your sideband filter. So your sideband filter design becomes easy, right? And you can. Now, are any questions arising in your mind when this kind of thing is being suggested? What kind of questions now arise in your mind to carry our discussion forward? Any questions that arise? Any other?
The demodulation.
Yes. The issue is, can such a signal, when how will such a signal be demodulated, and will it actually yield empty or will it yield something else, right? Because we have done something funny. Is this kind of filtering acceptable no matter what kind of filter you have here, right? Or there are some constraints, right? Well, the answer to that question is what we will now try to obtain, and we will find that the principle is fine, but you have to be careful in the design of this filter. If you want a demodulated signal which is proportional to empty, which is a replica of your message signal, right? So that's what you will like to understand. How should such a filter be designed? What should be the? I'm not getting into filter design. I'm getting into the what should be the nature of the transfer function of such a filter, right? Such that we are able to reconstruct our message signal back, because that's the ultimate requirement. The two requirements: one is we want to save the bandwidth, which we have done, right? Not by the whole amount of B, but more or less by a fairly big amount, right? For example, for the TV signals, this could be, let's say, 500 kilohertz, as compared to 4.5 megahertz. This is still a good saving, right? And so on and so forth. Okay. So what we will like to see is what is the nature of the modulated signal xt, where xt I am defining once again to be this signal here, right? So we will soon see. You see, in any case, it's obvious that now we can write xt in. Xt is a narrowband signal still. It's a bandpass signal. There is a center frequency, carrier frequency, and there is a spectrum around the carrier. So it becomes a narrowband or a bandpass signal, right? If the carrier is large enough frequency, and we know a general representation for any narrowband or any bandpass signal is the in-phase and quadrature phase representation, right? There is an in-phase component which is a low frequency signal, so x sub I t cosine omega c t minus x sub q t sine omega c t, right? That quadrature representation. So obviously the SSB signal had that representation. The VSB signal also will have that representation. The only things that will change are the actual values of x sub I and x sub q, the actual nature of the in phase and quadrature phase components. So we can certainly will be able to see that this signal that we have generated will have this form. Once again, this carrier part which I have introduced is because we want to be able to do envelope detection in the same manner that we did for SSB, right? So this part will be the same as we have for the SSB, plus of course there is a carrier that I am introducing here, minus a by 2 into some low pass signal y of t sine omega c t, where y of t will be, we will see soon, will be a function of both the message signal and its Hilbert transform. It will not be just the Hilbert transform of MT, right? So we can have this kind of representation, and if this kind of representation is possible, we can do perfect synchronous demodulation or approximate envelope demodulation, right? So first we'll discuss how this comes and then we'll discuss it. What about the transmission bandwidth? Here will be B plus beta, where beta is typically less than B, most of the times much less than B. Now demodulation is what we would like to spend some time on, because that leads to some crucial questions and answers. In the process, we will also look at a general theory of sideband filtering, which will include SSB as a special case, right. So VSB is a general case and SSB becomes a special case in which beta is equal to 0, right. So we will in the process also discuss a general theory of sideband filtering. Okay, and the general theory basically tries to answer the following question, right. The question is, let's say I have this modulator which we have just talked about, MT AC sine cosine 2 pi FCT, followed by a suitable band pass or high pass filter or low pass filter depending on what kind of band sideband you want, and that gives you your modulated signal x of t, right. And you get this x of t here, the demodulator, multiplied with AC prime cosine 2 pi FCT and for demodulation what do you normally do? Put a low pass filter here, right. That is your synchronous demodulation, and you will get a demodulated signal. Let us call it V sub OT, and the general theory that we are going to discuss addresses the following questions. Question: what kind of band pass filter should I use, or what kind of high pass low pass filter should I use at the transmitter? What kind of HF should I select so that V naught T is proportional to MT, right? Because we are suggesting some rather complicated filtering here, right, in the VSB case. So what kind of filter transfer function should this be? Suppose you want the upper sideband, so maybe let's say this could be a high pass filter, but any high pass filter or with some requirements, right, with some specific nature. What should be the nature of H of F excuse me, so that V naught T. So that is a question. Let me put it on the next page. Question: for what class of filters H of F will V naught T, V sub OT be proportional to the message signal? That is the question I would like to address. Okay. Okay. To do that, is the question clear to all of you before we start answering it? Before we start developing the answer for this question? The question is, you have some H of F here, like the VSB filter, right, which has this kind of characteristics. So we know generally we want this filter to be having a gradual roll off, but roll off can be designed in many different ways. For example, right, will any roll off be permissible, or will only certain kind of roll offs be permissible, right? Because otherwise I do know that this kind of a filter is quite fine, but is this fine for any kind of roll off, any kind of gradual attenuation, increasing attenuation, right? That's the basic issue we want to address. What should be the constraint on the filter, what should be the nature of the filter HF, so that if I at least do synchronous demodulation, there should be no problem and V naught T should be equal to empty. That's the question we are addressing. We do know one answer. For example, if there is no roll off, if the perfect filter, ideal cutoff filter, will get V naught T equal to K times empty. That one answer is known, but we want to develop a more general answer, right? And that's why you call it the general theory of sideband filter. Okay, to start doing that, let's look at the spectrum of the modulated signal, and we know that spectrum. Let me call this MT into AC cosine 2 pi FCT. I'll denote this by U of T, right? So then what is X of F? It is U of F into H of F, and U of F I know is the spectrum of the modulated signal, DSPSC signal, right? So X of F would be equal to U of F into H of F, which I know as equal to AC by 2, because U of F is AC by 2 into the message spectrum translated to FC plus the message spectrum translated to minus FC, that into H of F. That is the spectrum of your transmitted signal. What about the demodulated signal? Okay, again at the demodulator, I have called this the final output signal as V sub OT. Let me call this signal as V of T, the signal at the output of this product modulator, this mixer, right? So what will be the spectrum of VT? Your V of so if I define V of T as AC prime cosine 2 pi FCT times XT, which is what I am doing, your V of F will be AC prime by 2 into just the translation of this X of T, the spectrum of X of T. So X of F minus FC plus X of F plus FC, but X of F is given here, so can I substitute that here? How many terms will I get now? 4 terms. I'll shift each of these 2 terms. I'll find out X of F minus FC, I'll get 2 terms. Find out X of F plus FC, you'll get another 2 terms. You'll get 4 terms. So now out of these 4 terms, can I identify the 2 terms first, which will be in the baseband, because this is a band pass signal, isn't it? This this V of T is a band pass signal. Sorry, it has your X of F is a band pass signal. That's a modulated signal. When you are doing frequency translation of that, you will get a component translated around the 0 frequency and a component translated around the twice the carrier frequency. So can we identify those these 2 parts separately? These 4 parts that this will have, 4 terms that you will have here, will contain 2 terms which will correspond to the baseband component and 2 terms which correspond to the 2FC component. So let's first identify the baseband components. That will be AC into AC prime, right? Because you are substituting for X of F minus FC from here upon 4, right? What will be the baseband part? One component will come from when this becomes, so if I shift it to by plus FC, right, you will get MF, right, and that will become HF plus FC, and similarly from here if I shift it by minus FC, so I will get MF into HF minus FC. So M of F will be common in these 2 terms, and this will be H of F minus FC plus HF plus F plus FC. Is that clear? These 2 terms? What about the two FC terms? Same amplitude a sub c prime upon 4. So what will you get here? You are shifting this to the right by fc, right? So this will become mf minus 2fc. So I don't think I'll have a common factor now. Excuse me. M of f minus 2fc, and what will be the corresponding h factor? H of f minus fc plus m of f, this will come from here and we are shifting it to the left again by fc. So this will become m of f plus 2fc into h of f plus fc, right? Please see this carefully and see that you are convinced. So essentially what we are saying is this is the low frequency part of V of f and this is the high frequency part of V of f, which will be centered around 2fc, and you can see that this is obviously centered around 2fc because m of f was a low frequency spectrum, so you are shifting it to 2fc. What about hf minus fc? Hf was centered around fc and you are shifting it further to the right by fc, so it gets centered around 2fc, right? So this is centered around 2fc, this is also centered around 2fc, and everything is centered around 2fc, whereas this part everything is centered around 0. Okay, if it is all right, then I can proceed further. So if I have that low pass, now if I look at the output of the low pass filter in the demodulator, what will I see? So therefore V naught f, that is the output of the low pass filter, which term will you see? The first term, first two terms, right? So you will get an output which is AC prime upon 4 into m of f into h of f plus fc plus h of f minus fc, right? That's what you will get, and that provides the answer we are looking for, right? What do we want? We want our V naught t to be proportional to mt, k times mt, right? So what should be the, what does that tell you? What can we say about the filter HF? What condition should it satisfy so that this happens? This function of frequency which is coming from these two terms, which are coming from the filter transfer function, they should be equal to a constant value, right? They should not be a function of frequency, right? That's what it means. That is the condition we are looking for, that HF minus FC plus HF plus FC should be a constant. Let's for convenience call it twice HFC, because it doesn't matter what you call it. It should be basically a constant, and for convenience I'm just saying that let that constant be equal to twice the value at FC, right? And if I specifically choose the response of the response of the filter transfer function at f equal to fc to be, let's say, equal to half, right, then this condition becomes is equal to 1. Basically I'm choosing the constant to be equal to 1 arbitrarily, right? So the filter should be such that this condition is satisfied if you want that your demodulated output through synchronous demodulation actually is a replica of the message signal. So we need to examine what this condition means, right? And also we like to also address the question still of what is the actual representation of the VSP signal like in the time domain. So these are the issues we'll continue in the next class. Thank you very much.